Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to lecture 3.5 where we are going to review certain useful properties of Fourier transforms. Now in this I do not mention discrete time or continuous time because the properties that we are going to discuss are equally applicable to both domains. But since I use the term Fourier transform, obviously we are referring to the class of aperiodic signals. There exist similar properties for the Fourier series case, but we are not so particularly interested in them right now. So, the objectives of this module is are to discuss the properties of the discrete time and continuous time Fourier transforms, and in particular those that are relevant to time frequency analysis. I only highlight the utility of these properties. We will actually apply them when we study the particular tools such as short time Fourier transforms, wavelet transforms and Wigner-Willi distributions. Now just to recap, we have in the last 4 modules studied the 4 different types of theoretical transforms, the continuous time, periodic and aperiodic, and the discrete time periodic and aperiodic signals cases, where we have the Fourier series and Fourier transform cases. In all this we have really avoided the derivations and rather stated the results. Occasionally we have shown the derivation of some results, but by and large we have kept away the derivations, primarily because this is a unit where we are reviewing the concepts rather than learning them fresh. In fact, these are, as I have said earlier, also prerequisites, but we are just revisiting them in the context of time frequency analysis. We will adopt a similar approach here as well. We will learn the properties rather than trying to derive them, but a lot of these properties can be actually derived by hand without referring to any text, and in fact that would be a good exercise for you to go through. So just a few opening remarks as usual. To recall, one of the prime purposes of working with transforms is that they provide ease of analysis. So for example, if you take Fourier transforms, they are very useful in the analysis of linear time invariant systems and signals emerging from these systems in a number of different ways. Of course, we are not going to really study all the useful applications of these properties, but we will restrict ourselves to time frequency analysis, and in particular among the many properties we will focus on the time shift, time reversal, scaling, convolution, and as a consequence correlation properties of the Fourier transforms. We will also study the dual properties. I mentioned this earlier, we have seen this in duration and bandwidth as well. The time and Fourier frequency domains have a very nice duality, and so do these properties as well, as we will shortly go through. The main point that I would like to keep you in mind is these transforms are being reviewed with the purpose of analyzing and computing the other transforms that we are going to study in this course, including the Wigner-Willi distribution. Wigner-Willi distribution is not ideally a transform, but it can be viewed as a transform with an adaptive basis. So let us start looking at the linearity property, which is a fairly obvious result to derive. So if I have 2 signals with Fourier transforms x1 and x2, then the Fourier transform of the sum of these 2 signals is the respective sum of the Fourier transforms. It is a fairly easy one to derive, and you should expect this because these are essentially the Fourier transforms are essentially summations and they are linear combinations. So this property should not be surprising. Of course, this is this works behind the scenes in all the Fourier analysis and even the analysis of other transforms and so on. So the first it is second, but really the first property that we are going to use in the analysis of other transforms is the time shifting property. Now, this time shifting property states that if I have a signal whose Fourier transform is let us say a signal is x1k and its Fourier transform is x1 of f, then when the signal is shifted in time by a certain amount d, then the Fourier transform is multiplied with e to the minus j 2 pi f d. This result is, as it is stated, is given for discrete time signals, but as I mentioned earlier, it is equally applicable to the continuous time case as well. So, the way to remember this is the time shifts result in frequency domain modulations. Now, this is a very useful result in delay estimation, widely used in signal processing and so on. We shall use this property to study the transforms such as wavelet transforms and short time Fourier transforms, particularly the wavelet transforms. For example, if I translate the wavelet function, then how does it Fourier transform, its Fourier transform modify and so on. So, we will learn the particular application of this in the respective time frequency analysis tools later on. An important point to remember is time shifts do not affect the energy spectrum. This is also true for power spectrum as well. So, the energy spectrum of the shifted signal remains unchanged, obviously, because if you look at the Fourier transform of the shifted signal, the magnitude of the Fourier transform of the shifted signal and the original signal are the same, because the magnitude of e to the minus j 2 pi f d is unity regardless of the value of d. Therefore, the energy spectrum will remain the same, however, the phase is affected by this delay, and it is this property that is used in delay estimation. There are a number of classical delay estimation methods formulated in the frequency domain based on this property. So, you exploit the phase to estimate the delay. In fact, the spectrum shifts by minus omega d at each frequency, or you can say minus 2 pi f d. The phase shifts by minus omega d or minus 2 pi f d at each frequency. Now, the duality of this result is that a shift in frequency. So, this is just a reverse case. Now, shift in frequency corresponds to a modulation in time. That is the nice duality that these properties share. Now, once again I leave this to you to prove these relations. It is fairly straightforward. So, you start with the definition of Fourier transform and then evaluate the Fourier transform of the shifted signal and make some necessary adjustments. In about 1 or 2 steps you should be able to derive the final result. This is so both these properties are going to be useful to us later on. The next property of interest is the time reversal. By time reversal we mean reflection in time. So, if I have a signal whose Fourier transform is x of f, then the Fourier transform of the reflected one is the complex conjugate of the Fourier transform of the original signal. So, reflection results in a complex conjugate behavior. Remember, complex conjugate is obtained by replacing j, the imaginary part of the number, with its negative value. So, you are really transferring the negative sign in time to the imaginary portion. And the duality also, so if is also contained in the statement. So, if I am asking, if I reflect in frequency, what is the consequence in time? The consequence in time is that I am reflecting in time, right. So, that is because if I reflect the frequency, it is equal to taking the complex conjugate. So, the dual is contained in this statement. This is useful later on in writing an expression for the computation of wavelet transform. In fact, all wavelet transforms are actually rewritten in frequency domain using this property, but and another property as well. Okay. Now, coming to one of the most interesting properties to us, particularly in the context of wavelet transforms, is the scaling property. This is a property that needs to be understood well. So, we shall spend a few more minutes than we spent on the other couple of properties. So, what this result says is, if I have a signal whose Fourier transform is x of f, then the Fourier transform of the scaled signal, what we mean by scaling is, if I have x of k, then the scaled version is x of k by s, as you can see here. Then the Fourier transform of this scaled signal is x of s f. It is a fairly easy result to prove. Again I am avoiding the derivation here, but the simple the starting point is the expression for the Fourier transform. So, what you want to do is you want to evaluate the Fourier transform of the scaled signal, write the expression for the scaled signal, and then you should be able to make a change of variable. Just one change of variable will get you this result. So, it is a fairly straightforward result to prove. Rather than worrying ourselves about the proof at this moment, we shall ask what is the consequence of this property in time frequency analysis and in filtering and so on. So, if x of capital F, so now I am referring to a continuous time signal here, if the Fourier transform of a continuous time signal has a center frequency Fc, then scaling the signal, that is a continuous time signal, by a factor 1 over s results in shifting the center frequency to Fc over s. So, let me explain this to you briefly on the board, and there is also an illustration of this point in the next slide. So, what this result says is, if a signal has the Fourier transform x of f, then x of t over s maps to x of s times f in the Fourier domain, all right, where s is the scaling parameter. Now, the statement there says if x of f has a center frequency Fc. What do we mean by center frequency? For now, imagine that x of f is a real valued quantity. If it is not, then you take the magnitude. When is x of f real valued? When x of t is complex, right. You can have complex functions, for example, when you are dealing with complex wavelets such as Morlet wavelet, then this function here or signal here is a complex one. If it is symmetric, then you should get a real valued Fourier transform. Either way, whether it is complex or real, I can look at the magnitude, and let us say that the magnitude of x of f has this kind of a shape, just for the sake of illustration. So, here I have the center frequency Fc. This is what we mean by center frequency. We can think of x of t or even x of k as the impulse response of band pass filter. Later on we will make this observation. So, scaling this signal by a factor of 1 over s results in x the Fourier transforming x of s times f. Obviously, now what happens is that the center frequency of this here of this x of sf, if I were to plot, then now this what I would see is a scaling of the shift of the center frequency by a factor of 1 over s. Okay. Now, to understand this, I have the illustration later on. Whether it shifts to the right or to the left depends on the value of s. If s is greater than 1, then the center frequency shifts to the left, right, because Fc over s is going to be less than Fc. If s is less than, so this is center frequency shifts to the left, and that is the reason I have not drawn it yet, how it looks like. And then when s is less than 1, the same thing here shifts to the right. Now, this left and right are with respect to the Fc, that is the center frequency of the original signal, all right. I have not drawn this, but I have drawn this for you in the slide. This is the basic point that I am trying to make there. Now, before we go to the next slide, it is important to understand what is the consequence of scaling this signal, that is how does the signal look like when I scale it. So, to understand this, let us take the simplest functions, although I am not going to use this as in the next slide, I am going to use a different function. But to understand the consequence of scaling, let us say that the signal of interest has this shape like that of a Haar wavelet, and let us say this is 0, half, 1. We are not particularly worried about the magnitude, but we can say here this is 1 and minus 1 just for the purpose of discussion, that is really irrelevant. Now, when I look at x of t over s, suppose s is 2, all right. Suppose s is 2, then what happens is I have a dilated signal, which means I am really taking the signal and stretching it like I stretch an elastic band. Why does it get stretched? To see why it gets stretched, define this x of t of s as some x bar of t, just to understand what is happening. So, this is a new signal x bar of t, we have just introduced a notation which is related to this x of t through this relation x of t over s. So, let us say I am asking what is the value of x at 1, at time 1, x bar at time 1 at t equals 1. Now, because s is 2, I am going to replace s with 2 here. As a consequence, I have x bar of 1 as x of half, which means what is happening here, the value at half. So, if I were to draw the x bar as a function of time t, what happens is the value at 1 for x bar is actually the value at half, all right. So, let me actually draw a longer time axis because it is going to be a dilated signal. So, here I have 0, half, 1 and 1.5 and 2. So, the value at 1 for x bar is the value of x at half, which is actually 0, and the value at 2 likewise is going to be of x bar at 2 is going to be the value of x at time 1. So, which means at this point I am going to have this here. So, I am just showing you the crossover points here, and symbolically it will look like. So, you can see clearly that I have an elongated or a dilated signal, and now I leave it as a simple exercise to you to see that values of s less than 1 will result in compression. So, you are really compressing the signal. Obviously, what is happening is that the area under this is going to be more than the area under this. So, one needs some kind of normalization and so on, and we will talk about this when we discuss wavelets. So, the point to remember is when I scale a signal this way and values of s greater than 1 will result in dilation or elongation, and values of s less than 1 is going to result in compression, all right. And in frequency domain the same story is happening. Well, why? Because there is one more thing that I will show you. We have discussed here that the center frequency shifts to the left for values s greater than 1, right. So, what is happening here is the moment I elongate this, think of very high values of s, then what would happen is this becomes a really elongated pulse. So, it has much more lower frequency content than this one. So, this is changing fast, this is changing slowly. Whichever changes slowly we say it has low frequency, whichever changes fast has relatively high frequency, it is all relative to this original signal, nothing is absolute here, right. So, that is why now the center frequency is shifting to the left, predominantly this is a low frequency signal relative to this signal here, and that is why I have a center frequency shifting to the left when s is greater than 1. So, this is the new, this is fc prime, this is the center frequency of the scaled signal. Also, you should observe that I have the spread, I have the spread of the scaled of the Fourier transform of the scaled signal narrower than the one that I have for the original signal. Now, this is again a consequence of the duration bandwidth principle, right. What is happening here, when I am elongating this signal, I am extending the duration of the signal. As a consequence, I would be really narrowing the bandwidth, all right. So, what is the scaling factor here? The duration is being modified by this factor s, right. So, the duration is actually increasing. So, if sigma t is the duration of x of t, then x of t of s has a duration of s times sigma t. And the bandwidth here, if suppose x of f has a bandwidth which is a measure of the spread of this, it is not this exactly, but it is a measure of the spread, then the bandwidth of this is going to be sigma b over s. The product of these two is still sigma t times sigma b. Okay, that is the beauty of this scaling. So, now again you can see when s is greater than 1, I have a longer duration signal, but that results in a narrower bandwidth, and when s is less than 1, I have a shorter duration because I am going to compress this, but then at the cost of increased bandwidth. So, hopefully this gives you an idea of what we are going to see in wavelet transforms. So, let us see this with an illustration on the Morlet wave. I had shown you the slide in lecture 1.2 when we were giving we are going through an overview of wavelets. So, what I have on the top is the real portion of the complex Morlet wave. I could plot the imaginary one as well, and what I have on the right is mod x of f square. It reads power. So, it still curvature of this is the same as modulus of x of f. So, this is now the situation that I have for x of t. This is x of t, this is real part of x of t, and I have here mod x of f. When I scale it by a factor of 0.5, as I mentioned earlier, I have compression here, right. But then what do I have? I have the center frequency shifting to the right. So, what is happening here? Relative to the original filter or the original energy spectral density that I have, this now has the filtering characteristics in the higher frequency regime, because the center frequency has shifted to the right, but the spread has increased. Okay. And when I scale it by a factor of 2, which is greater than 1, then I have a dilated wave or wavelet, because now this is the mother wave and these two are the wavelets. I have a dilated wavelet. Now, the center frequency has shifted to the left and the spread has also decreased because of the reasons that I have explained there, all right. So, this is something that should be understood. There can be some confusion initially in understanding this, but again going through the exercise repeatedly, doing this by yourself will help a lot, and this is very important to understand how wavelet transforms really work. If you have understood this, you have kind of understood 50% of how wavelet transforms work, right. What is the basic idea? Okay. So, one of the penultimate properties that we are interested in is a convolution theorem, which is a very, very famous and celebrated result in linear systems analysis. Convolution in time domain transforms into a product in the frequency domain. So, if I have two signals and I am looking at a third signal which is a convolution of these two signals, then the Fourier transform of the convolution of this is the product of the Fourier respective Fourier transforms. It is a beautiful result because it paves way for a number of things, for a frequency domain analysis of linear time invariant systems, for computation of convolution itself, because there exist efficient algorithms for computation of Fourier transforms by way of FFTs, fast Fourier transforms. I can first compute the in order to compute the convolution, this convolution here, I can first compute the respective Fourier transforms, multiply them and then take the inverse Fourier transform, I will recover the product. So, that is the beauty of this result, but that is in the computational side. In the theoretical side, this leads to the analysis of linear time invariant systems in frequency domain. We have what are known as frequency response functions and so on. We had a preliminary discussion of this in the when we were discussing the discrete time Fourier transforms and so on. As far as time frequency analysis is concerned, this is very useful in the computation of continuous wavelet transform. We can write the continuous wavelet transform as a convolution and then evaluate the continuous wavelet transform in the frequency domain. At this moment it may sound strange because wavelet transforms help you do a time frequency analysis, but then we are saying we shift to the Fourier domain and come back, but they are all interrelated, all right. So, we will see later on how this is used in the computation of CWT, the details of them. Now, the duality of this convolution result is a product. When I have a product of signals, and I am looking at the Fourier transform of that signal, then the in the frequency domain I have the convolution of the respective signals, right. Now, how is this useful? Well, product is a relatively easy thing to evaluate, so we are not really going to use in computation, but we are going to use this result in studying Fourier transforms of windowed signals. What we mean by windowed is segmenting, as we do in short time Fourier transforms and so on. Windowing not only occurs in short time Fourier transform, but also in the regular Fourier transforms of finite length signals. All the Fourier transforms that we apply in practice are for finite to finite length signals, and you can always view the finite length signal as a segmented version of the infinitely long signal that we are unable to observe. Therefore, this result is useful in asking what happens to the true Fourier transform, that is that of the infinitely long signal, when I take only a part of it, which is what I can do in practice, and evaluate the Fourier transform. So, how does the Fourier transform of the observed signal or the observed series relate to the Fourier transform of the theoretical one is the question, and that is nicely answered by this, and this is called windowing, and we can show this results in spectral leakage and so on. We shall talk about this when in the next module when we talk of discrete Fourier transform. It is also useful therefore in understanding how short time Fourier transform works. So, finally, we have the correlation theorem, which is also the Wiener-Khinchin theorem version for deterministic signals. Although Wiener and Khinchin gave the result for the stochastic signals, it is just a slight adaptation of those terminology here. So, the Fourier transform of the cross covariance function is the cross energy spectral density. We have seen this in the context of discrete time Fourier transform earlier, and also in the case of discrete time Fourier series. So, the expression here says that the Fourier transform, discrete time Fourier transform of the cross covariance function gives me the energy spectral density. Again, I have given you relations both in terms of cyclic and angular frequency. The figure on the right essentially tells you now 3 different ways of computing the energy spectral density. We have discussed this earlier as well, how this theorem or this result gives me a way of computing the energy spectral density. So, one way is the classic way, I take the Fourier transform, take the magnitude square. The other way is through the Wiener-Khinchin theorem. Now, the way to prove this result is to actually take the to express the autocovariance function or the cross covariance function as a convolution between the signal and the reflected version of itself, if you are looking at the autocovariance function, or the reflected version of the other signal if you are looking at the cross covariance function. That is why I have a convolution of x1 and the reflected version of the other signal. So, that is of the signal itself. Then I have the autocovariance function and I take the Fourier transform, I can get the energy spectral density. The third route is to compute what is known as the discrete Fourier transform, which we will discuss in the next module, and compute the magnitude square. The discrete Fourier transform is concerned with the Fourier transform of a finite length signal. Now, when I increase this number of observations to infinity, then I can also recover the energy spectral density. So, there are 3 different ways of computing the energy density. In time frequency analysis, this result is very useful in understanding the Wigner-Willi distribution. So, with this we come to a close of this module on the properties of Fourier transforms. As I have mentioned early on, although we have stated the results for discrete time signals, aperiodic signals, these are also useful for continuous time aperiodic signals as well. And I suggest that you derive some of these properties by yourself. They are fairly easy to derive by hand without actually referring to a text. Of course, our teaching assistants and myself, we are always available to help you with the derivations or the answering your questions on the forum. Good luck and see you in the next module. Thanks.